I'm Jamie Schmeiser, and I will be your presenter for this virtual tutorial. I have been a member of the IBM Compiler Group, located in Toronto, for almost 20 years on and off since 1992. My current focus is loop optimization in LLVM, and I will be presenting ways that I have discovered for understanding optimization in LLVM. This tutorial, Understanding Changes Made by a Pass in the OP Pipeline, is being presented as part of the 2020 LLVM Virtual Developers Meeting, being held October 6th through 8th. This talk is divided into two parts. The first deals with existing ways of understanding LLVM optimizations, a brief overview of terms and concepts relating to compilers and LLVM will be presented. This will be followed by a discussion of ways of understanding optimizations being done by the compiler through the use of various options. Finally, special passes in the op pipeline will be considered. In the second part of this tutorial, new ways of examining the IR as it progresses through the op pipeline will be considered. This will culminate in a demo of one of these new methods. Compilers are typically divided into a front end, here Clang or Clang++, and a back end, here LLVM, where the front end has several phases dealing with ensuring that the program is correct. The front end produces an intermediate representation of the program that the back end optionally optimizes and then uses to generate code. Optimization is optional, and the default is to not optimize unless requested. There are various levels of optimization, which may consist of different optimizations, different orders of optimization, or optimization during different phases. Here, we are only interested in optimization of the LLVM IR before code generation. LLVM has multiple meanings, but here it typically means the LLVM IR. This is a machine-independent intermediate representation of a portion of code, which we will typically look at in a text form. The LLVM reference manual can be found online at the location shown. Passes are sections of code that may or may not transform LLVM IR. They typically will do a single or related set of transformations on the IR. They can work on different units of code. For example, they may work on the module, or functions, or loops, or other units of code. Passes take valid IR in and produce valid IR. A pass that does not produce valid IR is considered broken. An op pipeline is a series of passes strung together. A section of IR is possibly transformed by a pass, with the output being the input to the next pass, continuing down the chain of passes. The flow of control is handled by a pass manager. Understanding optimization is understanding how the IR changes as it flows through the pipeline. This means one needs to know what changes a pass makes and what order the passes are called. There are two pass managers with different calling conventions for the passes. Most older passes support both conventions, but some newer ones may only support the new pass manager. The legacy pass manager is the default, but it is being phased out. The new pass manager can be accessed from Clang or Clang++ using the option -F experimental new pass manager. The opt executable is a utility program that allows a custom pipeline to be built and tested. The desired passes are specified in the options. The pipeline will be set up to use one of the two pass managers based on how the passes are specified. Opt also supports options that allow one to examine the IR. Such options can also be accessed when using Clang or Clang++ by prefixing them with the option -m LLVM. The output from opt is the transformed IR, but if you are only interested in the output from the options that show the IR, the disable output option can be used to suppress the final output. Also, capturing or redirecting the standard streams on Unix can be used. There are several reasons to examine the opt pipeline and how the IR changes. The first is debugging. There may be a bug that needs investigation. Secondly, it could be for new development. One needs to understand if the code is working as expected. Or third, you might just be learning. You might be learning simply for the sake of learning, or in support of debugging or new development. This sample C program will be used throughout the tutorial for examples. It consists of a function that has a loop to do a summation and a main function that calls this summation function. To get the initial IR to feed into the opt executable, the command on the right part of the screen can be used. Note the gotcha. One must specify that the code should be optimized, or attributes will be placed in the IR such that the passes will not optimize it. There are several existing ways of determining what optimization is being done. First, there's debug information. Secondly, there are statistics. There are options to the opt pipeline that show the IR. There are also special passes that graphically show the IR. There's also an optimization remarks emitter, but this is only mentioned here for completeness and will not be considered further in this tutorial. The compiler will print debugging information when -debug or -debug only equals some ID is specified. This is an ad hoc method that reports whatever developers thought might be useful for debugging the code. Specifying -debug will result in all debugging information being generated, while -debug only equals ID will limit it based on the ID. Each file may have a macro, debug type, in it that names an ID. If this ID matches the one specified, the code in any LLVM debug macros in the file will be run. This code typically consists of a single statement that usually just sends something to dbgs, which is the debugging stream. However, any code can be specified in the LLVM debug macros, including multiple statements. Be careful that you do not accidentally introduce code that has side effects within these macros, as the code will only be run when debug is specified. Using -debug only requires inspection of the code to determine the ID to use, and to also understand what the debug output means. One can add new code to a pass to help understand it, and this technique can be very useful. In particular, calling dump on different values can be very useful in understanding the code. This slide shows a portion of the output from the example command shown on the previous slide. Approximately 350 lines of output is produced, but as you can see, it can be cryptic and some knowledge of the code would be useful to understand what this output means. Here, only a portion of the output is shown, with ellipses showing parts that have been removed. The stats option will produce statistics about optimizations performed. Again, it is an ad hoc method, as the statistics produced are based on whatever the coders decided to record, if anything at all. This also relies on macros placed within the code. The statistic macro takes an identifier and a string. The identifier is declared as an integer counter that can be incremented whenever a particular event occurs. At the end of execution, any non-zero statistic counters will be reported with a name and accompanying string. This can give insight into whether an optimization succeeded in transforming the code, as well as indicating how many attempts were made at applying a particular transformation. Statistics can be particularly useful for quickly determining whether a transformation was successfully applied when testing your code. Rather than examining the resulting IR, one can grep the statistics option for the string and associated count to quickly determine whether the code in question was successful in applying its transformation. This slide shows a sample set of statistics. It indicates how many times various optimizations were performed on the code. The IDs in several cases give good clues as to which pass did the transformations. Two powerful options, print before all and print after all, allow one to examine the IR as it enters and leaves each pass, respectively. These options are supported by both pass managers, and they will cause the portion of the IR that the pass operates on to be printed to the debug stream. A banner is printed before each section of IR, and this banner can be used to divide the output into portions of IR that were operated on by the pass. All banners start with 3 stars followed by IR in capital letters. This sequence of characters is not valid LLVM, so it can be used to search for banners. Note that just using 3 stars is not sufficient for filtering or searching, because there is valid LLVM IR that contains 3 stars. The command shown on the upper right portion of the screen can be used on Unix systems to count the number of passes called by the pass manager. Banners prefixed with hashtag are actually from CodeGen passes rather than optimization passes. The CodeGen banners can be filtered out using the command shown on the lower right portion of the screen to obtain a count of the number of optimization passes that ran. These two options can be used together to have the IR printed before and after every pass. This allows one to determine whether a pass changed the IR and what the changes were. However, there are 2 problems. First, the volume of output generated. Since output is generated before and after every pass, for every unit of IR that goes through the pipeline, a large compile can result in tens of thousands or more units of IR being output. Secondly, the section of IR may not be complete. Since a pass need not necessarily operate on the module, the unit of IR may have references to declarations that are not included in the IR shown. For example, the IR for a function may refer to a global variable. Since the IR is not complete, the executable will not accept the IR as input. This slide shows a portion of the output from the print after all with Clang using the new pass manager. Numerous portions of the output have been replaced with ellipses for demonstration purposes. It can be seen that the IR starting at the third instruction in the for.conn.block has changed. I've shown the changes in red on the slide. It isn't easy to locate in the output, in particular because the previous pass is a module pass, while the inst combine pass is reporting just the summation function. The filter print funcs option is a supporting option for print before all and print after all that limits when an IR is reported. This option takes a comma-separated list of function names and causes print before all and print after all to only print when the IR is for an indicated function. Note that the mangled name must be used in the list for IR from C++ code. When specifying multiple functions with this option, the IR produced must be examined to determine which function the pass was operating on, since the banner does not indicate this. The print module scope option modifies the IR printed by print before all and print after all to be the module, regardless of the portion of IR that the pass acts on. This has the benefit that the IR can then be used as input to the opt executable, but this can increase the size of the output significantly. The first option previously shown, filter print funcs, limits the amount of output to those passes acting on certain functions. The print module scope option ensures that the output is complete and can be used as input to the opt executable. The two options can be combined to get an IR that can be used as input to the opt executable for a specific function, which can then be brought up in a debugger or examined in other ways. Note that the LLVM IR produced can be reduced manually using an editor. For example, a module may contain several functions, but if you are only interested in one of them, the other functions can be removed, or perhaps changed from definitions to declarations to shrink the amount of IR. This technique can be very useful for developing unit tests for your code. The print before and print after options take a list of passes, and the IR is only printed appropriately for those passes. This works with the opt executable using the legacy pass manager, but does not appear to work with Clang or Clang++, as the option processing complains about the option. Also, it does not work as expected with the new pass manager, but work is in progress to address this. As one might expect, this option can be combined with other options to help limit the amount of IR generated. When one knows which passes in particular are interesting, these options can be used in place of print before all and print after all to greatly reduce the amount of output. The techniques shown so far can be combined. For example, one could start by examining the output from the stats option from the command shown. By grepping for the string in the code, we find that at least some of the source for this pass is likely in the file shown, and that there is likely more related code in the containing directory. Then, using a command similar to the one shown, we can use print before and print after to examine the changes to the IR. Since the statistics told us that 6 instructions were combined, it is likely that we will find some changes to the IR. The stats command also gives us the ID to use with debug only. Finally, two special passes allow one to generate a graphical representation of the IR. These analysis passes are inserted into a custom pipeline and will generate a file for each function. These files contain instructions for the dot utility. This allows dot to create a representation of the control flow graph in various output formats, such as PDF or JPEG. PDF is useful for large graphs as it scales well. JPEGs are really only useful for small graphs. The two commands shown on the slide illustrate how these passes can be used. The first command creates a custom pipeline consisting of the .cfg pass, along with some passes such as verifier passes that are inserted automatically by the pass manager, and gives it our sample LLVM input file. Since we are not interested in any output, we just send both standard out and standard error to dev null. The .cfg pass will create two files in the current directory. The names of these passes will be prefixed with dot, followed by the name of the function with the extension dot. So in this case, we will get two files, one named .main.. and .summation.. One for each function in the input. These can be discovered on Unix systems using ls-a, where -a tells ls to list all files, including hidden files which start with dot. The second command then invokes the dot utility, giving it .summation.. as input. -T PDF specifies that the output should be created as a PDF file, and the -O option names the output file. Shown on the right is the output from the commands on the previous page, while the illustration on the left shows the result when the first command specifies .cfg only rather than .cfg. The basic blocks in the IR are represented by blocks in the graph, while the flow of control is represented by the directed edges. .cfg only produces just the control flow graph, while .cfg has the LLVM instructions shown in the corresponding blocks. This view of the IR is very helpful as the flow of control is easily discernible. One situation where these special passes can be very helpful is when used with existing unit tests. Unit tests typically consist of small, custom pipelines with reduced IR as input. The invocations of opt in the unit tests can be modified to include these special passes to help understand what the tests do and how the passes being tested actually work. In summary, in this first section of the tutorial, we have examined 4 different ways of determining what the opt pipeline is doing. We have considered debug information, statistics produced by the passes, options for printing the IR, and special passes that can be added to the opt pipeline. While these methods are powerful, they do not completely satisfy the needs of the optimization developer. Debug information is useful when developing new code, but often the necessary information is not available when investigating a bug in existing code. Statistics may indicate how many times a particular optimization was performed, and the associated ID may hint at the pass, but it does not indicate the IR that was being acted upon. While complete raw data is produced by print before all and print after all, the interesting parts are difficult to find in the large amounts of output. Filtering methods or print before and print after can be used to limit the amount of output, but there remains the major limitation that there is no indication of whether a pass actually changed the IR. One must extract the bits of the IR and do comparisons of the before and after IR until the instance of a change is discovered. The graphical representations created by .cfg are intuitive and useful, and can be especially helpful once the interesting pass and relevant IR are determined. However, determining the pass and relevant IR can be difficult. In the second part of this tutorial, new ways of determining how the IR changes as it passes through the op pipeline will be presented. Several new options will be discussed, each presenting different ways of focusing attention on interesting aspects of optimization. These build on each other and will be presented in order of increasing sophistication, culminating with a demo of a powerful new way of viewing the changes to the IR and op pipeline. At the time of preparing this tutorial, the code for these new options is under review in Fabricator. With luck, it will have landed by the time of the conference. If not, it will hopefully land soon after. Since it is still under review, aspects of it may change, but the concepts presented here should probably stay intact. Note that these new options are only supported by the new Pass Manager, and thus require an appropriate pipeline in opt, or the F experimental new Pass Manager option being used in conjunction with Clang or Clang++. The first option, Print Changed, addresses the biggest difficulty with print before all and print after all. Like print before all and print after all, every pass will have a banner printed, but only those passes that actually change the IR will have the IR printed. The banner indicates the pass, the name of the IR, and whether the pass changed the IR. It filters out some Pass Manager grouping passes, invalidated passes, and passes that do not change the IR, just printing banners in these situations. The option respects the filter print funcs and print module scope supporting options. A new supporting option, filter passes equals list of passes, is also introduced that does analogous filtering of passes. This pass uses the identifier in the banners to name the passes. All of these supporting options can be combined. As a convenience, the initial IR is also printed at the start of the output. Here we see an example invocation using Clang and a portion of the resulting output. The output is truncated using ellipsis to show deleted parts. The start of the dump of the initial IR is shown, then a bunch of the output is omitted, followed by several banners showing passes that did not have the IR reported for various reasons. The Simplify CFG pass changed the IR, so the changed IR is reported. There are 6 different types of banners. Each of these banners begins with 3 stars, followed by IR in capital letters to allow for easy searching and recognition of the banners. The first banner indicates the initial IR. The other 5 banners all indicate the name of the pass and the name of the section of IR that was being acted upon. The banners indicate whether the pass changed the IR, in which case the IR is reported, or whether it was not reported and the reason why the IR was not reported. This can be because it was for an invalidated pass, it did not change the IR, or it was filtered out using a supported option. In the previous example, only 20 of the 207 passes actually changed the IR. The number of lines of output dropped by an order of magnitude from over 7,000 lines to 700 lines, while the size of the output dropped by 85%. The remaining 15% consists of the initial IR, banners indicating what the passes did or didn't do, and the IR after each change. Here we see part of a command that finds the banners indicating passes that change the IR. The part shown is a Unix pipe that finds the banners and then uses a stream editor to remove uninteresting banners. The output is shown below on the screen. Examining the banners shows which passes changed the IR, what portion of IR they were acting on, and the order that the passes made changes. This is often the first step in understanding what the pipeline is doing, and can be used as a basis for further filtering of the output using the various supporting options. As expected, it shows that most of the optimization was done on the summation function, with only a few passes optimizing main, most notably the inliner pass. The filter print funcs option can be used with print change to focus the output. Just a reminder that mangled names must be used with C++. For the example command shown, the amount of output is reduced by approximately 87%. The new option, Filter Passes, works with print changed and can also be used to fine-tune the output. In the example given, Filter Passes results in a 92% reduction of the output, focusing in on the times when a specific pass changed the IR. Here we see an example of print changed with multiple filters, in this case narrowing the output to the inliner pass on main. This is the output from the command on the previous slide. We see that main gets optimized to simply returning 15. There is a new hidden option, Print Before Changed, that modifies print changed to also print the IR before any pass that changes the IR. The usual filtering still applies, including other modifying options. This option has no effect unless used in conjunction with print changed. Another new option, Print Crashed, prints the IR as it existed before a pass that triggered an assertion or crashed. This option causes the IR to be saved before each pass, and a signal handler is registered to print out this saved IR. This is a convenience option, as the same IR could actually be obtained using Print Before All. But this option only prints the desired IR, while Print Before All prints the necessary IR at the end of potentially thousands of unnecessarily reported IRs. A new option, Print Changes, builds on Print Changed by combining Print Changed, Print Before Changed, and a comparison utility. When a pass changes the IR, a patch-like representation of the IR is shown. Those lines that are removed from the IR are shown prefixed with minus, while those added to the IR are prefixed with plus. The usual supporting filtering options are obeyed. The implementation of print changes relies on the availability of a Linux diff utility that supports line format commands. Unfortunately, I don't think that this is POSIX compliant and may not be available on all systems. Without this support, it will not work as expected. That said, it is still a very useful tool for understanding changes to the IR as it flows through the pipeline. Here we see an example usage of print changes with the filter passes option. The filter passes limits the output to invocation of the ints combine pass that change the IR. This pass does change the IR, so it is reported. A portion of the output is shown, and the change to the IR is easily identified with the minus and plus prefixes. The first instruction in the entry basic block is changed from a signed less than comparison to a signed greater than comparison. There are other changes made in the function, but they are not shown here on this slide. Let's look at another example of using print changes, this time with the simplify CFG pass. The slide shows the command and a portion of the resulting output. Here we see what happens when an entire block is added or removed. The entire block will be shown prefixed with pluses or minuses respectively. The branch instruction is changed, and we see that the basic block for.cond.for.endCritEdge is no longer reached. I highlighted this in red to help you to see it in the output. Below that, we see that two complete basic blocks, including the mentioned one, are prefixed with minus, so we know that these basic blocks have been removed by the pass. This represents a major improvement over existing methods of seeing the changes made to the IR. The IRs are only reported when they change, and the changes are clearly indicated in the IR itself. The final new option is the .cfg changes option, which combines aspects of print changes and the .cfg analysis pass visual representation. This option creates a website with all of the banners shown in a way similar to print changed or print changes. However, the banners for passes that change the IR are links to pages containing control flow graph representations of the IR, with the changes shown in the blocks. Unlike print changes, which shows the changes using minus and plus, .cfg changes shows the changes by coloring the elements that are removed in red and those that are added in green. Those elements that are unchanged are shown in black. By elements, I mean instructions, complete basic blocks, and edges between blocks. So, for example, if a basic block is removed, the block, its instructions, and the edges leading to and from the block will be shown in red. The option takes the name of an existing directory where the website is to be built. Since all links in the generated website are relative, the website should work if copied elsewhere. The main page for the website is called passes.html, and all the link pages are PDFs. The initial IR is shown as a collapsible box that can be expanded to links to the initial IRs for each function. Passes that modify a module have links to all of the functions, and they are indented and shown with a two-level numbering system to identify them as being changed by a pass operating on a module. The colors can be controlled using hidden options that take the name of the desired color. These names must be those listed in Appendix J of the dot guide, which is shown in the link. The .cfg changes option also requires a diff utility that supports line format commands, as well as the dot utility itself. I will now bring up the website generated using .cfg changes on our sample program. Here we see the website created by the command on the previous slide. Scrolling up and down the page, we see the banners listed, most of them being text, with some of them being links. At the top is a collapsible box representing the initial IR. Clicking on this expands the box to show links to the initial IRs for each function in the input. Each of these links show the initial IR for each function. This is the initial IR for main. And this is the initial IR for summation. As we can see on the main page, there are several banners that indicate passes that are ignored or are omitted because the associated pass did not change the IR. These banners are just text. The first pass to change the IR is number 6, Simplify CFG Pass. Clicking this, we see the CFG with the 4.inc block shown in red. It was removed by the pass, and we can see that the instructions from it were added to 4.body, as shown in green. The branches were removed by the pass and are shown in red. A new branch is added and shown in green. This view allows us to easily and quickly recognize that the instructions from 4.inc were removed into 4.body, and the now empty block was then removed. One nice aspect of this view is that visual patterns can be quickly recognized. An interesting pattern can be seen in the results from pass 24, inst combined pass on summation. Here we see the links from 4.const are both black, meaning that the links did not change. But the blocks showing whether the links are on true or false have both values in red and green. This indicates that the condition was replaced with its negation. We can also see this by looking at the changed instructions. The branch to 4.end used to be on false, but it is now on true, while the branch to 4.body used to be on true, but was changed to be on false. Other patterns become recognizable as one uses this view. Consider the results from pass 53 after loop rotate. Notice that this pass takes a loop as its input. Here we can quickly recognize that a loop guard and pre-header were added. The basic block 4.body.lr.ph was added, since it and the associated links are shown in green. This quickly becomes apparent on viewing the CFG. Scrolling down to pass 88, we see the results from a module pass. There's the two number the two-level numbering system, and the links are indented to show that this came from a module. Clicking on 88.0 shows everything in black, meaning that the main function was not changed by the pass. .1 shows various changes, including the removal of the loop, which can be easily recognized as the blocks of the loop are shown in red. Then, in 89.0, we see the summation function being inlined into main. From the previous CFG that we looked at, we saw that the summation no longer had a loop and was a series of computations. When inlining, the parameter becomes known from the call site, so the result can be, in this case, can be just computed. The body of main changes from a call to summation to just returning the value 15. Using these new options, .cfg changes in particular, one can quickly determine which passes change the IR, how the IR changes, and the steps taken to achieve the optimization. I've been working on some enhancements that are not complete yet. One is recognizing that the name of a value has changed and just showing the colorized old and new names beside each other in the instruction rather than showing the entire lines in red and green. Other enhancements may include different website layout. The code for these options is designed to be easily extended to allow new systems to be built upon it. There are base classes that handle the filtering and event calculations. One need only specify the code for handling how the various events are to be reported. The print changes option, for example, is implemented using about 100 lines of code, as most of the functionality is handled in the base classes. Perhaps you will extend the code to improve it, or develop other new ways of understanding the IR that will be more useful to you. In the first part of this tutorial, currently available ways of understanding changes made to the IR as it flows through the op pipeline were examined. These techniques included examining debug output, statistics, using options to the opt executable, and utilizing special passes to produce graphical representations of the IR. In the second part, new options were introduced that focused the output on the actual changes made to the IR. A demonstration was given of one of these options that produces a website with links to colorized graphical displays showing the changes made to the IR graphically. Hopefully, these new options will be available soon for general use, if they have not already landed by the time of this conference. Thank you for attending this virtual tutorial. Stay healthy and safe. Hi, everybody. We're here for the Q&A now. I'm Jamie.
Hey, this is Ettore. This was a very interesting talk. So let's start to ask some of the questions. See, there is a lot of questions already. So let's start from the one at the top. So very useful talk. The question is, what has been upstream for review already? So landed. And what is left yet to be upstreamed?
So the code for print changed has already landed. It landed last week, so print changed is already available. The other ones are still in the review process. Some have been reviewed, are at more advanced in the review stage than others. One of them has actually changed. The option for print crashed has actually changed to print on crash. Other than that, everything is still, the same as described in the video, but the only one that has actually landed is print changed. The others are still being reviewed.
Okay, so the next question is, are these slides available online? Some of the text is a bit small to read the 720p video.
That's something I'm not sure of right now. We've reached out to try and find the answer to management of the conference to find out whether or not it will be available otherwise. But I expect it should be, but I don't know at this time right now.
Okay, thanks. So, wow, lots of new options to filter the LLVM IR output. Which of the new options do you find most useful in your day-to-day development?
Well, they all have different advantages and disadvantages. The print changed is, I find, one of the most useful because it's also the fastest. It's the simplest, and it helps you to kind of find what it is that you're looking for very quickly. However, the one that I find most useful is the the .cfg changed, in that the visual representation that it gives, I find, is the most valuable to me for understanding what is actually happening. So, it kind of depends. If you're just looking for something very quickly to find out what passes actually did something, that sort of thing, then the print changed is actually more useful because it's much quicker. It gives you your results much sooner.
So yeah, on that I have a follow-up question. So when do you think that it's useful to use the other option, the option to visualize the graph or even the HTML website?
Well, as I said, I find that one to be the most useful when I've actually figured out that this is the path that I'm interested in, or this is the particular function that I'm interested in trying to determine what is actually happening, how a pass is actually changing the IR. Because the visual cues that you get, in the demonstration I gave some indication, you can see very quickly, you can see patterns. And the more you use that, the faster it is to see the patterns. And so you can look at it, for example, and you can recognize fairly quickly that, this pass removed this particular basic block and moved all of the instructions from that basic block into a different basic block. That can be seen very quickly and very easily with the .cfg representation. Whereas if you were using print changed, for example, it's harder to see that. You can look at the print change and the print change before, and look at the differences. Run them through diff or something like that, and you can see them. But it's not as easily, at least to me, to recognize that those are the changes. Now, also you could use the print changes, which gives you the diff automatically in there, and that's useful as well. But for me, looking at the visual representation of the graph is the fastest way for me to understand what's going on. And for those who have difficulties with the colors, I put in options to allow you to change the colors. I know some people have color blindness or challenges seeing certain colors. You can change them to whatever you want. You don't want them too bright, though. sometimes feels like it's going to burn out your retinas if you have them too bright. But
okay, thanks for the answer. So there was the next question is like about a limitation. So the new option do not work when using the legacy task manager. Is this a permanent limitation?
Well, at this point, it takes advantage of some of the structure of the new pass manager. The new pass manager has a callback mechanism that's actually structured into the pass manager that the whole thing keys off of. And my work, I'm only working with the new pass manager, so I only put it into the new pass manager because that's where I work. I haven't actually looked to see if that support is available in the legacy pass manager, because that's not where I concentrate on my work. Is it a permanent limitation? I don't know. I expect that you could put the same sort of support that it relies on. I would expect you could probably put it into the legacy pass manager, but I have not actually looked into whether or not that can be done. Now, some of the supporting things, like for example, the filtering of the passes, that could probably be put into the legacy pass manager. But I haven't really looked into that because that's not where I do my work.
Yeah, so there is a related question, I think that we answered. Is any plans to support backend passes as well? I take it by backend passes, the person that asked this question means the low-level optimizer, the LLC optimizer, and not just opt.
Right.
How much additional work would it be? That depends if he has, if you find those callbacks.
Right. If you find those callbacks, and also it would that's for the print changed and the print changes. The .cfg, that would be a considerable amount of work. The infrastructure that's there in the new pass manager that it uses makes it fairly simple to do straight textual type comparisons. However, when you get the print changes has some more infrastructure that it relies upon, but the .cfg that relies on the graph writer code that's already in LLVM, and the representation of that. There's a lot of infrastructure that goes into actually doing that code for presenting that view. The graph writer provides code for actually for writing out the graphs, but then how do you actually determine what the content of that graph is, and all of that. And how to call into the graph writer. There's quite a bit of code there. So to put that into LLC or whatever, you would have to have some sort of that support code to represent the changes at that level as well. So there would be a fair bit of code that would be required for that, for the visual representation.
Oh, and perhaps these changes are under code review to some of them still. So
yes.
Some of the suggestions for people that know LLC better than me or you do, they may have some suggestion how to extend to LLC, or they may want to contribute and extend it to LLC themselves.
Yes, yes.
Yeah. So then the next question is about the same. So this has been obviously there is the recognition from some of the audience that this would be extremely useful for do this on machine code. Find out what the registrar locator did. So we touched upon that. So for people that are interested into participating into the code review or propose new changes and feedback, can I access review the PR?
Right. Of course, they can review the PRs. They're up for review right now. After I could list them out. I could list out the numbers of the PRs, but it wouldn't be too useful. What I will do is after the Q&A, I will list the PRs, the numbers of the PRs so that people can access them. I'll put that into the written Q&A session so they can find the numbers there.
Okay. If I'm not mistaken, some of the options only have support for NPM, New Pass Manager. Yeah, again, do you plan to have support for the legacy pass manager? I think that there is a lot of people that want that code into the legacy pass manager, which is good because I think that people recognize that is useful. How did you stumble on this particular problem? What was your motivation on working on?
Well, when I first started working in Opt, I found that I wanted to know what the various passes were doing. And to try and find out what the passes were doing, you know, I first started using the print before all and print after all, but then I found that I had to constantly do the diffs, and I just found that I spent more time trying to figure out which passes actually changed something than, you know, than actually looking at it. You just kind of get swamped with how much is there, but it wasn't actually telling you whether something had actually changed. And so the first thing I did was I wrote scripts that did it, but then they were just so slow because there was just so many passes typically that you go through that it would have to be filtering out. And then, but I worked with that for a while. And I also worked with the .cfg. I found that very useful for understanding what was going on. But then at one point I was doing something, working on something, and I kind of stumbled across the mechanism that that was being used for print before all and print after all. And I thought, oh, wait a minute, I can put this right into the compiler. And I did, and the speed up was phenomenal and made it so much more useful. And then I started thinking, well, I wonder if I could do that. I actually wrote a script that would take the .cfg and compare two .cfg files and produce the sort of the visual display. But it was a script, and it took a really long time for it to run, just because it was a script. And then I also had a script that would do the generation of the series, but it was taking, you know, like hours to run on a fairly simple pipeline. And so then I thought, okay, well, let's put it right in there. When I found out about the .cfg, because I started thinking, okay, how would I put this in? And I found the graph writer code, and I thought, okay, this is how I can use this. I can do this using that. I had to change the graph writer code, which is some of the PRs that are up for review, to get the colorization, that sort of stuff. But that's kind of, I needed this to learn how the passes were working and to find out what things were happening. And then just kind of the visual thing, I like that. I found that useful. So that's kind of how I got in on that, going in that direction.
Okay, so talking about the new options, these new options do help reducing the verbosity of the IR and then help to focus only on which passes did make some changes to the IR. And that's great. Do you have any other idea on how to present the IR itself more concisely? And I think that to interpret this question, this is my interpretation, yeah, is, you know, it's not so easy to read LLVM IR. These are low-level instructions. Do you have an idea how to present this, you know, pretty verbose IR in a more concise and intuitive way?
Well, I tend to like the visual thing. I find it easier to understand. But at the same time, I also like kind of the idea of collapsing the information into kind of more easily understood packages, and also use that for filtering. So, for example, if you could have the you know, the .cfg representation rather than having, you know, the HTML kind of the HTML list that you click. What I really like is if you had something where it was kind of, this is the, you know, you have a picture of here's the the compilation. And then you click on that and it brings up, it expands out to, say, okay, a bunch of passes didn't fire anything. And then these ones fired something and then these ones didn't. So it expands like that. And then if you're interested in which ones didn't fire anything, you click on that and it brings up that list. But if you're interested only in the ones that did do something, you click on that and it brings up the passes. Then you click on that and then that would bring up, for example, a module, and the module itself would be, collapsed. You could click on that and then it would bring up all the functions, but each of the functions would be collapsed. And then you could click on that for which functions you were interested in, and it would expand out to be the basic blocks, and similar to the CFG only view. And then, which ones you're interested there, you could click on that, expand that, and, and there would be some sort of indication of the ones that actually changed and which ones didn't change. Maybe they would be in a different color or something like that for the ones that changed. So you could click on that to bring up which the actual instructions then. Something like that, it would be kind of an interactive expand and shrink of what the IR is, so that you could look at what you're interested in and filter out the things that you're not and move around. You'd end up clicking a lot, but it would help not overwhelm you with the amount of information that there is. That's one of the problems I find, is that the IR itself, it just gets overwhelming. It would be fairly simple actually to, for example, with the print changes, it's based on the basic block view with the changes in the basic block. If you wanted to filter out the basic blocks that didn't actually change things, it would be fairly simple to extend it to do that. In the same way, if you weren't interested in which passes actually didn't change the IR and you just wanted to filter all of that out without even getting that listed, again, the way the code is designed to be extendable and changeable. And it's got a series of base classes that handle most of the simple functionality with virtual function calls. So for example, if you didn't want to even have the reporting that a pass didn't change something, all you'd have to do is derive from the class and change the virtual function, and just override the virtual function that reports that banner and just suppress it. And then you'd have one that did not, that only listed the passes that changed. You'd be it would take you longer to write your test cases for that to contribute it than it would to actually to change the code to do it, because you'd be talking about 20 or 25 lines of code to make that adjustment. Your test cases for it would be the majority of your contribution in that case.
So, you mentioned that the IR, there is different way that you can zoom in into the IR and so on, and we've seen that into the, the website, the HTML file. So this is a question that is related to that. How long does it take to create the HTML files for a moderately complex application? So
that's an interesting question, and it really kind of points out the benefits of the different levels of comparison. I tried an example of using a compilation unit from a spec benchmark, right? It was about 411, I think, lines of code. But when you include all of the files and you pre-process it, you're talking about 48,000 lines of code, okay? And I ran it through the various things at op3. So not op2, but at higher op levels. And to compile it took 1 second. To run it with print change, now this is on my particular system. I didn't even check to see how loaded it was, but it should give you an idea of the order of magnitudes here. So print change ran in about 8 seconds. Print changes, which is calling out like about 8,500 times, because there's about 8,500 banners, calls out to diff 8,500 times, took about 2 minutes and 11 seconds. Now, .cfg changes actually blew my disk quota after generating over 9,000 PDFs. And that took about 6 minutes, which actually is pretty fast. And the passes.html was already at 12,000 lines of code. So it was probably fairly close to being done. But this kind of gives you an idea of why the filtering of all these things is so important and why the various levels are useful. You want to find out, you want a fast result, you use print changed. And then you use that and you use the filtering options to narrow in what it is you want. 6 minutes for generating 9,000 PDFs is actually, I think, quite fast.
But it's not always necessary. You start from, like narrow it down, and then you may diving into that level of complexity only when you need it.
Right. So you start out with the print changed, and you say, okay, I look at this a little bit, or the print changes, and you've determined, oh, okay, I'm interested in pass XYZ. And then you use the filter passes for XYZ, and that'll cut down, probably reduce it by an order of magnitude, the number of things that you're interested in. And then, okay, well, then I'm interested in this function. And then you put that filter on, and suddenly, instead of generating 9,000 PDFs, you're generating about 50 or 60. The sample that I used in the in the demo, which is, of course, it's obviously a Mickey Mouse example, but I don't remember how many things there were. I think I mentioned how many banners, like how many passes actually fired. But with that one, it was negligible, the amount of time that it took to generate the website. It's like, okay, if you compiled it, it returned instantly. But if you ran it with the .cfg changes, you noticed, oh, okay, it wasn't instantaneous, but you weren't waiting. It's not like you went to go and make a cup of tea or something. It was negligible, the amount of extra time it took. So if you do that filtering, you really want to use the filtering. That's why I added those filtering, to help you speed it up and to help you narrow down. A lot of this is about narrowing down and filtering out the stuff that you're just not interested in, and that makes it difficult to find stuff.
So I noticed the print change prints the banner for every optimization that run, not just the one that modified the IR, everything that ran, at least the banner has been printed. Would it make sense to just print the short ID instead? I think that, you print the short ID of each transformation. They didn't do anything. So just print that line, and then, oh, this transformation did something, print the code after the transformation ran.
So it prints the banner. Would it make sense to just print the short ID? So there isn't that much difference. You're still printing out a banner. If you wanted to just suppress the banner completely, I kind of described how you could do that. It would actually be fairly simple to suppress the banner completely. To change the banner to use the pass ID, there's work right now. The pass ID, there's some infrastructure work that needs to be done with the new pass manager to use the pass IDs. It uses the pass IDs as they are sent right now to the pass manager. And so if you're referring to the pass IDs that you would use for specifying print before those IDs, there is some work that needs to be done in the pass manager infrastructure itself to be able to have it refer to those pass IDs rather than the long names that we're getting in the banners right now. And there is actually a pull request that is being, so there is a pull request on working on that right now. So there is some work being done there. So in the future, it may be that the banners change from printing out the pass IDs as they are right now to just being those short IDs. When that work lands, that would pretty much change automatically because it's based on what the pass manager infrastructure is providing. If you change that, it will change this as well.
Okay, so, well, we have more questions, but looks like we are running out of time, so it's time to wrap it up. Thanks, Jamie, for the great talk. And if the audience, if there are more questions that have not been answered, Jamie is going to answer them in the chat or try to answer them, and feel free to join the chat and continue to post new questions. We'll monitor the chat and try to answer whatever you need to, whatever you want to ask.
Great. Thank you very much for all the questions. I enjoyed doing this, and I hope you find it useful.